Welcome back. Let's look at rule number 2. That is, remove constants. Let's see what I mean. I've written here the most ridiculous function ever. The function is print first item, then first half, then say hi 100 times. Probably not the best named function ever, but as the name describes, all we're doing is we're going to console log the first item in the array, and then we're going to print the first half of the items. So I'm finding the middle index of the items. So I'm saying items.length divided by 2, and I use math.floor here in JavaScript as a way for us to make sure that we get a whole number, and we're going to say variable index is 0. I'm using a while loop here instead of a for loop, and I'm saying as long as middle index is greater than 0, I want you to console log the items. So that means console log the first half of the items. So if we had 10 items, I'm going to console log the first 5 items. And then I'm going to do another for loop and say I'm console logging hi 100 times. Pretty useless, I would say. Not a very useful function. What is the big O of this function? Well, looking over here, it's going to be big O of 1 over here. So we have 1 for just logging the first items. Then we have half of whatever the items is. So in our case is n divided by 2. Because even though we have a for loop or a while loop, we're only logging half the items every time. So we can just do n divided by 2. And then finally, we're doing a for loop. But again, this is a bit of a trick. We're not looping over the items array. We just have 100. No matter how big the items array is, this is going to be always 100. So I just say plus 100. It's another step. Because again, we're just adding each of the steps that we see here. So this is our big O for this function. But rule number 2 states we want to drop the constants. We simply are saying that we don't really care that this big O is actually n divided by 2 plus 101. Remember, in an interview, we only care about the things that we saw on the chart. Nothing specific like this. So this turns into 1, and this, even though it's divided by half, in the grand scheme of things, we only care about when it scales, when the inputs are getting larger and larger. So as n gets bigger and bigger, we don't care about adding an extra 100, because if n is 1,000,000, adding an extra 100 on there, another 100 steps, doesn't really matter. And same with dividing by 2. As n gets larger and larger, dividing by 2 has a decreasingly significant effect. So we drop the constants like this. So this becomes O of n plus 1. Okay, and because 1, if n was 1,000,000, is very insignificant, we can just drop this as well. This function just becomes O of n. What if we had another function that had, let's say, O of a plus 50? Or a of 50 with a ton of zeros. It doesn't really matter. We drop the constants. It's going to be O of a. What about this other situation? What if we have this function here, compress boxes twice, where this function actually has 2 for loops, where it does the same thing, but it's 2 for loops. So we have O of n in this for loop, and then O of n in this for loop. And because these are 2 separate steps, well, we add them together. So it becomes O of n plus O of n equals O of 2n. But again, in an interview, this doesn't really matter because we drop the constants. And if we drop the constants, what does this function equate to? Well, it's just O of n. To prove that I'm not lying to you, if we look at this function on our graph, we see that the elements, as the elements increase, we have two operations because we have two for loops. If we have two elements, in that case, we do four operations. If we have three, then we do 1, 2, 3, 4, 5, 6. And you see how it increases. But at the end of the day, even though the line is steeper, we have a lot more operations to do. The way the line increases is still linear. And that's the key here. With big O, we don't really care about how steep the line is. We care about how the line moves as our inputs increase. Makes our lives a whole lot simpler, doesn't it? So remember, drop the constants. You're never going to really see numbers in big O notation. Most likely the notations that we've seen in the past before on our graph. Usually these, and the only time you see numbers is when you have O of 1, O of n squared, or O of 2 to the power of n. Which we'll get to later, don't worry. I'll see you in the next video.